In this video, I'll be discussing the questions which I had posted in my Facebook page, Understanding Concepts of Physics. So, there I had posted this first boost series. So I will be discussing the questions on the question and answers on your boost 1. Okay. So the first question says, why don't leptons have isospin number? Okay. So isospin, right? So this is for question number 1. Isospin is related to your charge independent nature of your nuclear forces, right? So what do I mean by charge independent nature of nuclear forces? So for instance, in your electromagnetic force, my proton is positively charged and my neutron is neutral, right? So my neutron is neutral for my electromagnetic interactions and proton is positively charged. Whereas the same thing, when I do it for strong interactions, right? When I am doing it for strong interactions, my proton and neutrons are not identified as charged particles. The positive charge and the neutral charge of protons and neutrons are not identified by your strong interactions. Hence, we introduce the concept of isospin, right? Because the strong interaction, they are charge independent. Hence, we introduce the concept of isospin. So that's how the concept of isospin came into picture. So here the question says, why don't leptons have isospin number? And first, what are leptons? So leptons are your electrons, right? Muons, tauons, right? And their respective neutrinos and antineutrinos, right? So electron and neutrino, muon neutrinos, tau neutrinos. So these leptons, they do not take part in strong interactions. So leptons, they do not feel strong interactions. So leptons are not going to feel strong interaction. Hence, they do not have the concept of isospin, right? So they take part only in your strong interactions and weak leptons take part only in your strong electromagnetic interactions and weak interactions. Hence, we do not have the concept of isospin for leptons. So that is the answer to your question number 1. Question number 2 is rather an easy one. So which says that the beta decay, right, and your force which holds the neutrons and protons together. So the beta decay, weak interaction is responsible for beta decay and strong interaction is responsible for holding the neutrons and protons together in a nucleus. So the third question is, what is strange about strangeness particles? So what is so strange about them? First, they are produced in associated manner. So they are produced in associated manner. So they are produced in associated manner, meaning, suppose you have pi minus and p and they are giving me some strange particles. Okay. So now when they are produced, so these two are strange, right? So this is a hyperon, this is a kaon. So these two are strange particles, and when they are produced in associated manner. They are not produced singly. And also the second point is, they are produced via strong interaction, right? But when they decay via weak interaction. So when these strange particles decay, they decay via weak interactions. Okay. Now the fourth question is, why cannot we have lighter particles decaying into heavier particles? Okay, so let us assume I have some particle P which decays into Q, R and S, right? So from energy conservation, suppose P is decaying at rest, I have my rest mass energy of P equals to rest mass energy of QRS, right, and the kinetic energy. K denotes the kinetic energy for your Q, R and S. Okay. Now, if my kinetic energy is 0, right, in case my kinetic energy is 0, then I have my MP equals to MQ plus MR plus MS. So, if my kinetic energy is 0, then the mass on this side should be equal to the masses on the other side. And if my kinetic energy is non-zero, right, meaning a positive quantity, I cannot have it as negative because it's a kinetic energy. So, K not equal to 0 will give me MP greater than MQ plus MR plus MS. So, these two equations suggest that my P has to be heavier. I cannot have the other way around, right? I cannot have lighter particle decaying into a heavier particle. I must always have a heavier particle decaying into a lighter particle. So this is from your energy conservation. Okay. So now moving on to question number 5, which says that are quarks fermions or bosons? So quarks, they are fermions. The answer is the quarks are fermions because they obey your Pauli's exclusion principle. Okay. So now the last question, 6th one, is your E minus E plus going to gamma, and your other one is E going to pi plus gamma. Okay. So now these two interactions, they look okay if I look via charge conservation, right? But still these interactions are not allowed. First is because this violates momentum conservation. This violates momentum conservation. I'll tell you how. So, momentum conservation tells me that my initial momentum and final momentum should be equal, right? So, if I'm in the rest frame, if I'm doing my calculation, say in the center of mass frame, where the total momentum of the initial particles, the sum of the momentum should be equal to 0. So, in my center of mass frame, my total momentum must be 0, right? So, momentum conservation implies that my PF should also be equal to 0, right? But because this is gamma, and I know for gamma, P gamma equals to h by lambda, which is equals to h nu by c, and this term h nu is not equal to 0, right? Hence, my final momentums from momentum conservation and from the property of gamma is not equal. Hence, this is violated by your momentum conservation. So, it's like you have your electron coming from one direction and positron coming from one direction, right? The two momentums cancel, but your photon is moving in one direction. So, nothing is there to cancel this momentum, right? So, this interaction is forbidden by your momentum conservation. And the last one is, you have your P proton going to pi plus and gamma. So, the first thing you can check is baryon number conservation. For a proton is a baryon, hence the baryon number is 1, and pion is not a baryon, right? Hence baryon number is 0. Gamma again is not a baryon, it's exchange particle, so it's 0. So delta B, this side is 1, B here is 1 and on the other side is 0. So delta B is not equal to 0. Hence this is not this is violated by your baryon number conservation. Thank you.